In this lesson we're going to look at the extraction of aluminium. So aluminium comes from an ore found in the Earth's crust called bauxite, which looks like this. And in order to extract the aluminium from it, the bauxite is going to be crushed and purified, and we're going to end up with a powder of aluminium oxide. Okay, so we have aluminium oxide here. Now we remember that in the reactivity series, if we look at the oxides of the various metals, that the bond strength of the metal oxide increases as you move up the series. So we remember that in fact silver and gold are pretty easy to extract because they don't form oxides with anything, so they occur naturally as the pure metal in the Earth's crust. And then when we come to mercury oxide, well, all we need to do is just heat that compound and it will decompose directly into mercury and oxygen. And then after that it becomes a little bit harder. Between copper and zinc we're going to use a method called reduction, and to do that we're going to mix the oxide with soot, that's to say with pure carbon, and we're going to heat the oxide, and the carbon will reduce the metal oxide to the pure metal. Now that can only happen if the metal in its oxide is below carbon in the reactivity series. So we can't use this process of reduction by carbon if the metal is above carbon. These metals are more reactive than carbon, and the bond strength of their oxides is too strong. So we're going to have to use another process called electrolysis in order to break the metal oxide bonds in these metals. Okay, so for aluminium up to potassium we're going to use electrolysis. Now aluminium oxide in its powder form, in its solid state, will not conduct electricity. So in order to use electrolysis to extract the aluminium, we've got to change it into its molten state. Right? So we need to heat the aluminium oxide to form an electrolyte. That's to say a liquid which will conduct electricity. Now the problem with aluminium oxide is that it has a very high melting point. That's over 2000 degrees Celsius. So in order to melt the aluminium oxide we have to mix it with another substance called cryolite, which is also a compound of aluminium, but the melting point of this mixture is typically round about 900 degrees Celsius. So this makes the process of electrolysis of aluminium oxide much more economical, because it requires less energy to produce the electrolyte. So let's have a look at how the process of electrolysis works. So this is our electrolysis cell here, and you notice straight away, well, we've got the power supply here, we've got the positive, and that's connected to what we call the anodes here. These are the anodes. Now in this type of cell, the housing of the cell is connected to the negative of the supply, so this is called the cathode, and this has a negative electrical potential. So what we're doing is we're melting the aluminium oxide using the cryolite to help us. Okay, and what will happen is that when the aluminium oxide is heated to its fused state, it will dissociate into aluminium ions and oxygen ions. So you've got Al2O3, that's the formula for aluminium oxide, that will become Al3 plus O2 minus, so we're going to have 3 of those and 2 of those. Okay, and here we've got the aluminium and oxygen ions in the fused aluminium oxide. Let's put a 3 plus on each ion and 2 minus on each oxygen. Okay, so the positive metal ion is known as the cation, and the cation will be attracted to the cathode. The negative ion is known as the anion, and the anions will be attracted to the anodes. So what happens then is that the positive aluminium ions are attracted to the cathode. Okay, they move down this way, which is the casing of the electrolysis cell, and likewise the negative oxygen ions are attracted to the anodes. Right. Negative is attracted to positive. Okay, so first of all let's have a look and see what happens at the cathode. Well, here the aluminium ions are attracted to the negative cathode, and when they reach that they pick up, or they gain, each ion gains 3 electrons to form aluminium. Okay, so what we get here is a layer of molten aluminium being formed along the cathode, being deposited on the cathode, as each aluminium ion picks up electrons from the cathode and forms the elemental aluminium metal, and that is in a molten state and will be extracted from the electrolysis cell. Okay, so we get our aluminium comes out here in a molten state. Now this process here which is taking place is known as reduction. Reduction is where an ion picks up or gains electrons. And we say that the ion is being reduced. Now at the anodes, the positive anodes, what's happening is that the negative oxygen ions, well, they're attracted to the positive anodes, and when they reach there they give up their electrons, so they lose their electrons to the anodes, forming oxygen gas and giving up their electrons to the anodes. So just to balance that equation, we're going to put a 4 here and a 2 here. Right, and we call this process oxidation. So oxidation is taking place at the anode, while reduction is taking place at the cathode. And when oxidation occurs, the ions lose electrons. That's to say, the ion, in this case the negative ion, oxygen ion, is oxidized. So we call this electrolysis reaction a redox reaction. That's right, it's known as a redox reaction. I'll write that up here. There's not much space left on this diagram really. So it's a redox reaction, and what that means is that there is both reduction and oxidation taking place at the same time. So you get reduction at the cathode, oxidation at the anode, a redox reaction. Now one thing I should have pointed out here before was that the anodes and the cathodes are both made of graphite. Okay, they're both made from graphite, and graphite is a form of carbon. It's an allotrope of carbon. So what happens here is when this oxygen gas is released at the anode, it immediately reacts with the carbon in the graphite to form carbon dioxide. Carbon dioxide is released, but the problem with that is, let's just write that equation. So you have the oxygen here released at the anode, immediately combines with carbon in the graphite anodes to form carbon dioxide gas. Now the problem with this is that the carbon in the anode gradually gets consumed by the oxygen, and as a result these anodes will eventually have to be replaced. So every now and then the graphite anodes need to be replaced as they are consumed by oxygen released during the electrolysis process.